friends, welcome to our podcast channel, The Storytellers. Stories about astronomy, the sky, the cosmos, motivation, music, history, and many things more.
Hello everyone. Our today's story is all about the different kinds of refracting telescopes. This type of telescopes are mainly made on the principle of refraction. Now what is refraction? Here the word may seem very unfamiliar to many, but I can assure you that most of us are familiar to the mechanism of refraction. Imagine the spectacles that we use in our everyday routine, or the sunglasses that we use on a sunny day. Every one of them are the examples of refraction. When a ray of light traveling in one medium enters another medium obliquely, the ray changes its direction at the interface. This phenomena is known as refraction of light. In case of spectacles or sunglasses, the thing that is responsible for this change in direction is the lens. The lens refracts the light in such a way that the light becomes suitable for the user. There are mainly two types of lenses, convex and concave. In case of convex, when the light falls on the lens, it gets converged to a single point after refraction. And for a concave one, when light falls on the lens, it gets diverged after the refraction. There are mainly two different types of refracting telescopes, such as Galilean telescope and Keplerian telescope. In the year of 1609, Galileo Galilei designed the first refracting telescope called the Galilean telescope. It used a plano-convex lens as a primary lens and a plano-concave lens as the eyepiece. In this telescope, the plano-convex lens L1 is placed at one end of the tube and the plano-concave lens L2 is placed at the other end. Let us consider an object AB situated at infinity. The parallel rays coming from the object will fall on the primary lens L1. Then the refracted rays will again fall on L2. In the absence of the lens L2, the refracted rays will meet at point X and forms the real image A'(B'). But because of the lens L2, the rays will get refracted again by L2 and enters into the eyes of the observer E. The observer will finally see the object as a virtual image A'(B') formed at the point Y. Using this telescope, Galileo observed the phases of Venus, craters of the Moon, and the four natural satellites of Jupiter known as the Galilean satellites. In the year 1611, Johannes Kepler introduced a small improvement in Galileo's design, and that telescope is known as the Keplerian telescope. In this telescope, a plano-convex lens L1 is placed at one end of the tube, and another plano-convex lens L2 is placed at the other end. Let us consider an object AB situated at the infinity. The parallel rays coming from the object will fall on the primary lens L1. Then the refracted rays will meet at the point X and forms a real image A'(B'). This image will now act as an object for the lens L2. The rays coming from the image will fall on L2 and the refracted rays will enter the eyes of the observer. The observer will finally see the object as a virtual image A'(B') formed at the point Y. Here the convex lens L2 in the eyepiece created a wider field of view. In spite of all these things, the telescope have a major disadvantage. A lens is nothing but a collection of prisms. Since the prisms can divide the white light into 7 different colors, the same thing also happened for a lens. The light gets divided by the small prisms, and as a result, the lens cannot converge the rays of all the colors in a single point. Hence, the final image becomes hazy. This defect in image is called chromatic aberration. The formula for magnification of this telescope is as follows. M equal to F naught divided by Fe. Here M stands for the magnification, F naught stands for the focal length of the primary lens, and Fe stands for the focal length of the eyepiece. Hence, if we want to magnify the image, either we have to decrease the focal length of the eyepiece or we have to increase the focal length of the lens. But the thing is not very simple. If we want to increase the focal length of the primary lens, we have to make bigger lenses. But that's a quite tough job. Since the lenses have glasses on both the sides, if we increase their size, they will get sagged by their own weight due to the gravity. That creates limitations for making large refracting telescopes. That's why most of the largest telescopes are made using mirrors. In the late 1890s, the Yerkes Observatory was built in Wisconsin, which houses the world's largest refracting telescope with a main lens that is 1.02 meters in diameter. So, that's all for today. Thank you.